hybrid projection methods with recycling for large inverse problem. So this work is joined with my postdoc advisor, Julian Chang and Eric Sturter. So when I was at Virginia Tech. So my presentation has 4 parts. At the beginning, I will introduce some backgrounds on the hybrid methods and show some disadvantage of this method, and which is also the motivation for us to propose this new method. And then I will introduce our proposed hybrid projection methods with recycling. After that, I will show some numerical results to compare these 2 methods. And finally, I will make some conclusions and show some future directions. So, so let's see what's the inverse problem at first. So here, if we, so here we have this rock picture. This is a very nice picture. And if we run some operator and we can add some noise on the picture and we get this noisy picture. So this whole process, we call it forward problem. But practically what we usually, the problem we usually face is we have this bad picture and we want to do the inversion. We want to do the denoising or reconstruction. So the opposite process, so we call it as an inverse problem. So in this work, we are interested in this linear inverse problem. So here B is the observed data, it's our observation, and A is a forward model, and it typically a very large matrix. And the X2 is a desired solution, which we want to compute, which we want to approximate. And epsilon is the additive noise. And usually we have some prior knowledge, such as statistical properties. For example, we usually assume epsilon follows some Gaussian distribution or Laplacian distribution. And our goal is given the observation as a forward model, we want to compute the approximation of the X2. So solving the inverse problem is not easy. So there are 3 main challenges. Firstly, the solution may not exist. The solution may not be unique, and the solution may not depend continuously on the data. So the third one means a little bit perturbation on the data or a little bit noise in the data will cause a very big change when we do the approximation of the solution. So for example, this one is a hockey bird. So this hockey bird is a mascot of Virginia Tech. And this one is a blurring image of this hockey bird. So we want to do the image deblurring. So, but if we do this process by doing the A inverse times the observation B, our result image will look like this. So here we can see the image is horribly corrupted by the noise. So which means for the inverse problem, we cannot directly do the inversion. So so for the inverse problem, instead of minimize this residual, we need to minimize this augmented residual. So there are many choices of the regularization part. So here the lambda is a regularization parameter. So the way to choose, there are many ways to choose a regularization term Rx. So the most common way is called Tikhonov regularization, so which is the L2 norm of the solution X. And if we want to mainly focus on the boundary of the image, or we can use a total, or the shape of the image, we can use a total variation regularization. Or if we have some prior knowledge about the image, like if the image is very sparse, we can use the L1 regularization. And currently, many people also use the data to know what is an appropriate regularization for some specific problem. So, and they use a neural network to know the regularization term Rx. And in this work, we focus on the Tikhonov regularization. So if we know the regularization parameter lambda, the Tikhonov regularization, the solution of the Tikhonov regularization will represent it like this. So, and here I also want to use a truncated SVD to explain why we need the regularization if we solve the inverse problem. So if we do the truncated SVD on the matrix A, so here the sigma I is a singular value, and U and V are the matrix with the orthogonal column or orthogonal row. So, and sigma is the singular value of the matrix A. So, and the sigma is ordered in the decreasing way. So here, if we check the value of the UI transpose times B, we can see this when the index I increasing, so the value, this value will decrease at first. And then if this, when the value touches the noise level, it will stabilize at this level, at this value. But if we check the denominator, the sigma I will keep decreasing and approaching to 0 because the matrix A is a yield post. So which means when the index I becomes very big, the coefficient will approaching to infinity because numerator will stabilize and some certain value, and the denominator will approach into 0. So that's why if we don't use the regularization term, the solution will become very horrible. So to avoid the keep increasing coefficient, we introduce this filter factor, which is defined like this. So here we can say if we choose some non-negative regularization parameter lambda, so when the sigma I approaching to 0, the phi I will also approaching to 0. So this filter factor can help us to kill this increasing coefficient. And so that's why we need this taken off regularization. Also, that's why when we solve the inverse problem, we need to do the regularization. So another point is also choosing a good regularization parameter lambda is also very important for us to get a good approximation of this problem. So here we can see if the lambda is very small, which means we trust more on our observation if the lambda is very small. So, but sometimes when the observation is very bad, for example, if there are much noise in the observation, our solution we get will not be good. But if we choose lambda too big, for example, if we can see if lambda approaching to infinity, the solution of this problem will approaching to 0. So which means if we choose a very, very big regularization parameter lambda, the resulting image we get will be close to a black image. So choosing a proper regularization parameter is very important for us to get a good solution of this problem. So here I also want to use this example to show like the choice of the regularization parameter is very important for us to solve this inverse problem. So this is also this deblurring problem. So here's this one corresponds to the lambda equal to 0, which means we don't add any regularization. And so since the observation is not good, so we can see the resulting image is very bad. But if we increase the lambda a little bit, we can see the mascot. At least we can see the mascot, which is much better than this one. So here, but we can see the background is also not that good. At least it's not very smart, not very smooth. So if we keep increasing the lambda a little bit more, we can see the background start to become very smooth. But we keep increasing lambda, we can see the whole image get over smooth because the lambda is relatively bigger. So, and the image become blurring again. So we can see this accuracy of the solution is very sensitive to the choice of the regularization parameter lambda. And here I list 4 popular way people use to choose a appropriate regularization parameter lambda. So here for the discrepancy principle and the UPRE, for this 2 method, here the sigma is a covariance of the noise. So which means if we know some statistical information about the noise, we can use this 2 methods to choose appropriate regularization parameter lambda. And for the GCV and WGCV, we don't need some prior knowledge of the noise. But for this 4 method, we can see we all need to solve this optimization problem. And the size of the optimization problem is the same as the size of the original inverse problem. So which means if the inverse problem becomes very big, finding a good regularization parameter lambda will become very expensive. So that's why for the large scale inverse problem, choosing a good regularization parameter lambda will be very expensive. So for the large scale inverse problem, people usually use the iterative method to solve it. For example, here I listed the relative error of the conjugate gradient. So the relative error is defined as a difference between the numerical solution and the true solution scaled by the L2 norm of the true solution. But if we check the relative error of the conjugate gradient, we can see this method is semi-convergent. So which means the error will decrease at first, and then it will increase again. But in practical problems, since we don't know the true solution, so it will be very hard for us to find a good stopping iteration. So that's why people introduce this hybrid method. So which means they want to do the iterative regularization. They want to regularize this problem iteratively. So to avoid the semi-convergence, the iterative regularization, the relative error of the iterative regularization will perform like this. We can see this method is converge. So that means in the practically we can choose any number of iteration as we want to stop this method, and it will not get diverge again. So for this problem, so this method will be more stable than the conjugate gradient. So the idea of the hybrid method is we use some Golub-Kahn bidiagonalization to project the original large size inverse problem onto a small size projected problem. So given the forward model A and the observation B, we'd use the initialization using the observation like this. And then at each iteration, we only do the matrix vector multiplication to get the U and V. So at the iteration M, we can get this important equation. So here the VM and the UM plus 1, they have the orthogonal columns. And the number of columns is only related to the number of the iteration. And for the projected matrix BM, we can say is a bidiagonal matrix. And the size of the matrix is M plus 1 by M is also only related to the number of iteration. And usually when we use this hybrid method, the number of iteration is usually 100 or 200. So which is much smaller than the size of the original inverse problem. So the projected size of the projected problem will be very small. And based on this important equation, we can project the original problem onto this small scale projected problem. And we can see the size of this problem is M plus 1 by M. So solving this problem will be much easier than the original problem. So for solving this problem, since the size is very small, we can use any method we want. We don't have to use the iterative method to solve it. And after we solve this problem, we get the projected solution Y, and then we map the solution back to get the solution at the M iteration. So this XM is a solution of the original problem. And since the projected problem is the size is very small, we can use the way we introduce, like the GCV, WGCV, the UPRE, to choose a appropriate regularization parameter lambda to solve this projected problem very well. And also, for the projected matrix BM, so there are many theoretical to prove that the property of the BM is very similar to the property of the A, since the largest singular value of the BM will be very close to the largest singular value of the A, and smallest singular value of the BM will be very close to the smallest singular value of the AM. Of the A. So which means since they have the similar largest singular value, so the BM also contains the most important information of the operator A, and also A is yield post, and so that's why the BM is also yield condition. So for the projected problem, is also a yield post problem. But we can see the BM, the size of BM is much smaller than A, but BM keeps the most important information of the forward model. And since the projected problem size is very small, we can apply the standard techniques to choose a good regularization parameter lambda to solve this projected problem very well. And then we can map the solution back to get the solution for the original inverse problem. So the whole process of the hybrid method is given the forward model A and the observation B, we can apply the Golub-Hahn bidiagonalization to iteratively project the original problem onto this small scale projected problem. And then we can apply the techniques to solve to get a appropriate choice of the regularization parameter lambda, and then we can solve this projected problem very well. And then we can map the solution back to get the solution of the original problem. And the mapping is defined as a VM times YM. So, and the VM is based on the Golub-Hahn bidiagonalization we introduced before. So here the problem is if we since we need to map the projected solution back to the solution of the original problem, we need to save this large matrix VM. So here, although the number of the columns is related to the number of iteration, so the number of columns of the V is a small m, but the number of rows of the V is related to the size of the original problem. So here we can see the size of the VM is capital N times M, and so the capital N will be very large. So the capital N is the same as the length of the solution of the original problem. So there are many cases. In these cases, the storage cost of the VM will be very large. So the first one is for some image deblurring problem with a small noise level. For this kind of problem, it has a slow convergence. So which means we need many iteration to get the problem converge. So which means we need to save many large vectors. So in this case, saving the matrix VM will become very expensive. The second case is like a very large linear system, for example, like a dynamic problems. If our image is 3D and plus a dynamic plus a time, so our problem will become 4D. So for this kind of for these cases, the length of the solution, the length of the basis vector will become very long. So in this case, usually the computer doesn't allow us to save many vectors like this. So in this case, if we have a storage limit, so we cannot run many iterations. So, and the last one is even if the storage allow us to run many iterations and the large number of iterations, when the iteration number becomes large, it will also cause a projected size of the projected problem large. So in this case, solving the projected problem will not as fast as before. So to address this issue, we propose as a hybrid method with recycling. So the idea of our proposed method is we want to since saving the VM is very expensive, we want to compress the VM to the WK. So here we want to reduce the columns of the VM. So we know the hybrid method is also Krylov subspace method, and the Krylov subspace is a solution space of the solution we are searching. So, but in the Krylov subspace, we don't think every basis are the same important. So here we want to select some most important basis and then remove the less important basis. So this is the whole point of our method. So we want to reduce the columns of the VM and compress it to the WK. And all our compression is also based on this important equation. So, and the equation is from the Golub-Kahn bidiagonalization. So the first two methods are based on the low rank approximation of the projected matrix BM. Since we know the BM is also like a yield condition matrix, so we can do the low rank approximation such as truncated SVD or reduced basis decomposition on the projected matrix BM. So when we do the low rank approximation, the number of the column of the BM will become smaller. And based on this equation, we can reduce the number of columns of the matrix VM. And the second category of the problem is we select the important columns of VM by checking the solution of the projected problem. So after we solve the projected problem, we get the solution YM. And then when we map it back, we can see we're mapping by doing the VM times YM. So we check each element of the YM. So the large element means the corresponding column in the VM is more important, and the small element in the projected solution YM means the corresponding basis is not important. So we keep the basis corresponds to the large element in this vector YM, and remove the basis corresponds to the small element in the YM. And we call this solution-oriented or sparsity enforcing compression. So the second one means we solve the projected problem sparsely. So which means the projected solution YM is more sparse. So it will be easier for us to identify more important columns if we use this way. So after that process, we can compress the matrix VM to the WK. Since we changed the solution space, so we need to modify the original Golub-Kahn bidiagonalization process. So at the beginning, since we changed the solution space, which means we need to augment our solution space based on some basis vector WK. So we do the QR factorization on the AWK, and then we change we modify the iterative process in this way. So here by these two equations, we can see all the iterative process is related to the change the solution space WK. And then we can also as the L iteration, we can get the matrix, the equation like this. And we can also do the projected matrix, the BL is also bidiagonal, but for the whole process, the projected matrix is not bidiagonal again, but it's upper triangular. Since the solution consists of two parts. The first one is the change the solution space. WK is the one we compress. Is a basis we compress the VM. So, and another one is a VL, is our newly augmented solution, the basis vector. So, and the C is a coefficient of the basis in the WK, and D is a coefficient of the basis in the VL. So the new solution corresponds to the two different solution bases. And then we also do the projection. We can see the projected matrix is like this, and R is based on the QR decomposition, and the R is upper triangular, and the BM is bidiagonal. So now the projected matrix is not bidiagonal again, but it's upper triangular. So it's also okay because the size of the projected matrix is very small. So even if it's a dense matrix, solving this problem is also not expensive. And we can see the size of the matrix is K plus L plus 1 times K plus L. And this number is pretty small. It's also not related to the size of the original inverse problem. And then we can solve this projected problem, and we get the solution CD, and we map it back to get the solution X, and which is the solution of the original inverse problem. So the whole process of the hybrid projection methods with recycling is we can run the original hybrid method at first, and we can so when the matrix VM, when it reaches the storage limit, we can compress it to the WK, and then we can based on the WK, we can run our modified Golub-Kahn bidiagonalization process to keep augmenting our solution space. And then we do the projection and solve the projected problem and keep doing the augmenting. So if the number of the basis vector reach the storage limit, we do the compression again. And then we still do the augmenting. So each time when the number of the solution space touch the storage limit, we always do the compression until we reach the stopping criteria, and we output the X. So for the whole process, we also find at the beginning, if we don't have to run the original hybrid method if we have some prior knowledge about the problem. So the WK can also be the prior knowledge of the problem. For example, if we want to do the reconstruction of the image about the tumor. So, and the tumor is changed each month. So if we want to do the reconstruction of the tumor in the February, we can include some prior knowledge of the tumor in the January. So this prior knowledge is not related to the current observation, but we can include it as a prior knowledge, and the prior knowledge can be included in the WK. So the WK at the beginning doesn't have to be the compression of the VM. So it can also be the prior knowledge we want to include. So we'll also do some theoretical analysis of our methods. So here I show some easy theorem here, and in the paper there are more complicated, theoretical analysis. So the first one is we approve our projected matrix and the original projected matrix, they have the interlacing property. So which means their singular value is interlacing with each other. So which means the property of the projected matrix of our method is close to the property of the matrix of the original hybrid method. So their largest singular value will be close, and their smallest singular value will be also close. So that means even if we do the compression, we didn't lose much information. So here, and all this theory is based on the truncated SVD compression. The second one is we check the Frobenius difference of their Frobenius norm. We can see the upper bound is decreasing as the iteration increasing. So that means when the iteration increasing, the Frobenius norm between of these two matrices will become close and closer and closer. So for the numerical results at the beginning, we try this a very typical image deblurring problem. So the size of the image is 256 by 256, and we choose a noise level very small, like 0.2%. So which means we said that for the small noise level, the image deblurring problem will converge very slowly. So and we check we compute the relative error to compare the numerical methods, and since our method is to address the situation of the storage limit, so here we assume the maximum storage is 50. So which means that we can at most save 50 length of vectors, 50 vectors, and the length of the vector is 256 square. So we can at most save 50 this kind of vectors. And here the maximum storage for the compression is 30. So because it's hard for us to set up a tolerance of the compression strategies. So here we means we have to compress, we have to reduce the columns of the VM to some certain number. Otherwise, this algorithm will not keep going. So we have to compress the VM, reduce the number of columns of the VM to at most 30. So we have to remove at least 20 columns here. So for this problem. So here we can see in the left figure, we can see if we check the relative error, so the blue one is LSQR, which means we don't include any regularization. So we can see it has a semi-convergent. And for the red one refers the original hybrid method, and the regularization, we use the WGCV to choose a regularization parameter. So since our storage limit is 50, so we can say it stopped at 50 iteration. And since it reached the storage limit, it will not keep decreasing. And for our hybrid recycle method, we can see when it touches the storage limit 50, we do the compression and then we do the augmenting. So this algorithm will keep going and keep going, and we can run it as many iterations as we want. So the right figure is a storage. So storage here means the unit. So unit is defined as if we save one scalar, the unit is 1. So and the storage of the vector it means a number of the elements of the vector. So we check how many storage we need. For the hybrid method, since we don't do any compression, we can see it keep increasing as the number of iteration increasing. But for the hybrid method with recycling, since each time when we touch the storage limit, we do the compression and then we do the augmenting and then we do the compression again. So we can see the storage is always below some certain number. So we can, which means we can run any number of iteration as we want, and is always below some certain storage. So we don't have this issue. So here, if we check the error image means we use the reconstructed image to minus, we use it to minus the true image. So the darker means a larger error. So we can see here for the hybrid method, since it stopped at 50, and since it touched the storage limit, so it stopped. This problem needs to be stopped. So we can see the error is larger than the hybrid recycle. Since the hybrid recycle, we don't have this issue, so we can keep running this method until it converge. So the second method, the second example I want to show is the CT method. So for the CT, there is a common sense that it's hard for us to do the CT scanning from 0 to 360. So it's impossible for us to do CT like all around. So usually the CT will have the limited angle problem. So which means we get the CT data piece by piece. So here we assume we get the CT data in 2 pieces. So the first one is from 0 to 89. The second piece is from 90 to 179. So we have this limited angle problem. So for this kind of problem, since we get the data piece by piece, we can formulate the mathematical model like this. So the B1 refers to the data from 0 to 89. And B2 refers to the data from 90 to 179. And we need to solve this sequential problem, like this linear system. And solving this linear system usually is very expensive for the practical problem. So what people usually do is they solve this two problem, like A1x equal to B1 and A2x equal to B2. They solve these two sub-problems separately, and then they average the solution to get the solution of this problem. So that's an alternative way for the people solve a large practical problem. But here we introduce this hybrid method with recycling. So which means we can solve the first sub-problem like using the original hybrid method. And when we solve the second sub-problem, so we can use the information, the solution information from the first sub-problem. We can use it as a prior image. So we can include it when we solve the second second sub-problem. So when we solve the second problem, since we include some information from the first problem, we can use the hybrid recycle method. So here, and we compare our method with so here we can see the pink one is a hybrid method with all the data. So which means we just solve the large the whole system brutally. So of course we can get the most accurate solution, but practically we cannot do this since this process is very expensive. So here we can also see the CPU time is the largest. And for the hybrid method with recycling is our proposed method. We can see the solution is the accuracy is very close to the most accurate one, but for the time it's much faster since we do the compression if we touch the storage limit. So, and then if for the hybrid method for the second data, which is a -1. So since we only use one piece of the data, we can see the accuracy is pretty low. And the blue dot one is the way people usually use, which means the average of the solution of the two separate problem. We can see this accuracy is also lower than our method. And we also compare our method with the algorithm proposed by Christian in 2019. And in their method, the idea is also included some prior knowledge in the hybrid bidiagonalization process. But for their algorithm, we find like the prior, their method is very sensitive with prior knowledge they include. So which means if the prior knowledge they include is not good, the algorithm will become very bad. So, but our method, the prior knowledge, the solution, the result solution is not very sensitive with the prior knowledge. So which means if the prior knowledge is not good, the coefficient refers to the prior knowledge basis will become very close to 0. So, and then I also provide the reconstruction image. So here we can see this one is the best one and corresponds to the smallest arrow. So which means it's a hybrid method for all the data, which is also the most expensive one. We can see the reconstructed image is the best one. But for our hybrid method with recycle, we can see these two reconstructed image are very similar. At least we can see the details of this is a Shiplocan phantom. We can see the detail of the Shiplocan phantom very clearly. And for the average of the image, we can see there is some shadow of the reconstructed image. So the shadow is also prevent us to prevent us from saying the details of the image clearly. And if we only use a second data set, we can see we can only get half of the ship-Logan phantom. So, and the second one is we split we have more serious limited angle problem. So which means each time the data we get is 45 degree. So we have more sub problem. So we need to also solve this sequential problem, this linear system. So the idea is also very similar. Like we solve the first sub problem using the original hybrid method. And when we solve the problem in the later, we can include the information from the solution of the previous problem we solved, and we included as a prior knowledge when we solve the problem, when we solve the problem in the later. So and here we can see, since we have 4 sub-problem, so when we run the hybrid method with recycle, we can see when we after we use the first data set, the relative error decrease like this, and then it decreases step by step. And each time when we include one more piece of the data, the relative error decrease step by step. So here we can see after we do the reconstruction from the first data set, we can get 1/4 of the ship-Logan phantom. And then when we use the second, when we do the reconstruction on the second data set, we include the information from the solution based on the first data set when we do the reconstruction based on the second data set. So here, since we include some prior knowledge from this image, we can see we can get the half of the ship-Logan phantom. And then we include one more piece of the data, we can see we can get the 3/4 of the ship-Logan phantom. And finally, we include all the data, we can get the complete ship-Logan phantom. So this process, this example shows that our method can handle the streaming data. So in many cases, we cannot get the data, the whole data simultaneously. So we get the data piece by piece. So this our proposed hybrid method with recycle allow us to complete the reconstruction when we get more and more data, and we can do the reconstruction better and better. And here we can see when we have the more sub problem, so the most common way, like do the average of the image, the average of the solution become worse and worse. So it also shows in the reconstructed image, we can see the average of the solution, we can see it have more shadows here. So if we have more sub problems, if we use this method, we will have more shadows. So we also test our algorithm on the real data. So for the real data, we don't have the true solution. So we just compare the reconstructed image. So this is also a limited angle problem, and we get this sequential problem like this. So this one is a lattice root. So we can see the most accurate one is also, if we brutally solve this sequential problem, we can get the most accurate solution, the best reconstruction. But we can see the hybrid recycle method. This method can be applied in the practical problem. We can see these two reconstructions are very similar. But for the average image, we can see, since we have the shadow also affect the details of the image. And if we only use a second data set, we can get the half of the lattice root. And the second real data is based on the walnut. And the walnut, this one is a modified angle problem. So in some CT scanning cases, we cannot do the scanning like degree by degree. Sometimes we need to do some sparse CT, so which means we need to jump. Like here we do the degree 3, degree 5, degree 7, or degree 3 we need to do some jump. So like this. So we call it the modified angled problem. And for the modified angled problem, we also formulated the mathematical model in this way. And the way we solve this problem is also like we solve the first subproblem using the original hybrid method. And then when we solve the problem in the later, we can include a solution in the previous problem as a prior knowledge. And here we can see for the best one is also we brutally solve this sequential problem. For the hybrid method with recycling, the background is not good. Is not black. Is not the whole black. So, but for details of the walnuts, we can still see the details very clearly. And for the average of the solution, we can see it blurs the details of the walnut since it has some shadows, although it can do the background reconstruction very well. But here I believe people care more about the details of the object. And if we only use one piece of the data set, we can see the reconstruction is a worst one since we don't use the whole data. So in this work, we propose a hybrid method with recycling. So in this method, we can compress the Krylov subspace. So we can keep the most important solution basis and remove the less and discard the less important solution basis. And based on this process, we can save the storage. So which means we can run the hybrid method if we have a storage limit problem. And we also find this method can be applied if we need to solve this sequential problem. And it's also very convenient for us to handle the streaming data. So which means when we get more and more data, we can complete the reconstruction, making the reconstruction better and better if we get more data. So that's all of my presentation. Thank you for your attention.
Thank you, Jiahua.